All right, so when we talk about absolute or global extrema or extreme values or global maxima or global minima or absolute maxima or absolute minima, those are all the same thing. It just means it is the highest point or the lowest point on our function. Okay? The official definition is that our function for an absolute max, our function is always less than or equal to that maximum value for all of the values in our domain. D is just a domain. And for an absolute minimum value, it has to be that our function is always greater than or equal to that value for all of the values in the domain, which means that we can have multiple instances of the absolute max or the absolute min. So for example, let's take a look at the function in blue to start with. Our blue function, y equals sine x, and we're talking only about the domain 0 to pi. So what is the absolute maximum on the interval from 0 to pi of sine x?
1.
Yep, the max is 1. And where does it occur? At x equals what? Pi over 2. This is exactly what you would write. If I asked you what's the absolute max of sine from 0 to pi, you'd say it is 1, and you don't have to, but it would be nice if you clarified where it occurs at x equals pi over 2. If I asked for the absolute minimum on the interval from 0 to pi of y equals sine x, you would say that absolute minimum is
0.
0, and it occurs at, that's right, max, x equals 0, and at x equals pi. Right, it occurs 2 different times, and that's okay. As long as it's the same y value, no matter how many times it occurs there, we still call it a max or a min. Okay. Good? Everybody all right with that? Great. What about for the cosine function from 0 to pi? The absolute max is
1.
1, and it occurs at x equals, wrong, max,
0.
at x equals 0. And our absolute min ought to be
-1.
-1, and that should be occurring at x equals pi. Everybody good with that? So most important thing here is that an absolute min or an absolute max, there can be only one value of it, but it might have multiple occurrences. No issues? Everyone good? Spectacular. All right. So let's take a look at a nice, simple, easy function here. F of x equals x squared. So if we are looking at just the normal domain of this function, right, from -infinity to infinity, what is the absolute minimum?
Zero.
Okay, 0, right? And it occurs at x equals 0. What about the absolute max?
Infinity.
Okay, so it's approaching infinity and approaching infinity. Since infinity is not a real number, we will say that there is no absolute max. We don't even indicate that it's infinity. But yeah, it's going up to infinity, therefore no absolute max, because a max or a min has to be an actual numeric value. Everybody good with that?
Yeah.
Yep.
All right. What if we look at the closed interval from 0 to 2? What's our absolute max? If we just restrict the domain to 0 to 2.
4.
It should be 4. It should be at x Or, that looks horrible too. It's really hard to write on this stupid laptop screen. 4 at x equals 2. And what about the absolute min?
Zero at 0.
0 at 0. Okay, good. All right. Everyone okay with those? Those are the easy ones. Now, what if I have an open interval at 0, but a closed interval at 2? What is my absolute max? Should still be
4 at 2.
4 at x equals 2. But what about my absolute min?
Would it be approaching 0?
So it has to be an actual number, so we can't say that it's approaching 0. It is approaching 0. You're definitely right. It's definitely approaching 0, but since approaching 0 isn't a specific number, we can't state that. So is there a number that it does get to that is the smallest number that it does get to?
No.
No. So on this open interval, we would say there is no absolute min. And what if we change this to an open circle up here? For the open interval from 0 to 2.
No absolute maximum.
No absolute max, and also no absolute min, right? Neither of those would be the case, right? Wouldn't have one of either. Everybody good with that?
Yes.
Okay, cool. So we note that the only one of these where we had an absolute max and an absolute min was which one?
The closed interval.
Yeah, the one that was closed on both sides. There is no way for us to have a function that is continuous on a closed interval for it to not have both an absolute max and an absolute min. If we have a half open interval or we have a completely open interval, it's possible that you might not have an absolute min or an absolute max. It's still possible that you could, right? I could have something like this, let's say. This is continuous on an open interval, right? And it still contains an absolute max up here and an absolute min down here. But there are plenty of ways to draw it so that it doesn't have to. But if I close the interval off, no matter how I draw this, right? I can draw it however I want. As long as I close the interval off, it's got an absolute max. Looks like this one's right here. And an absolute min. And closed interval, we will always have an absolute max and an absolute min. And that is what we call the extreme value theorem. So the extreme value theorem says if you have a function that is continuous on a closed interval, then it will have both a maximum, an absolute maximum, and an absolute minimum on that interval. Okay. Everybody good with that?
Yep.
All right, so let's take a look at each of these real quickly for assuming these are all closed intervals here. For the first one here, it's got an absolute max, right? And it's got an absolute min, and they are both on the interior of the domain of this function. But we could have the minimum at an endpoint and the maximum on the interior. Or we could have a minimum on the interior and a maximum at an endpoint. Or we could have the maximum at an endpoint and the minimum at an endpoint. Everybody good with that?
Yeah.
Okay. So what about this last one down here? It's open on the ends here, but it's got points that it's defined for. Does this one have an absolute maximum and absolute minimum on this interval from A to B?
Yes.
No, it doesn't.
It's not continuous.
If f is continuous, only if it's continuous are we guaranteed to. So this one, We get very, very close to this value, but we never get to it. We get very, very close to 0, but we never get to it. And there are definitely values larger and smaller than these two endpoints that we actually have. Okay? So we're not guaranteed a max or a min, only if it is continuous on the closed interval. Everybody okay with that? Or?
Yes.
Cool. All right. So then when we talk about local extrema, so that's all we have to say about absolute extrema. We're going to go back to the extreme value theorem at some point in the next day or two and use it. But for now, we just want you to know what it is. So we're going to talk about local extrema. So local maxima and local minima just means that on some open interval, that point is the highest or the lowest point. So just because this point right here at B is not the overall highest point on this entire domain of our function from A to E, does not mean that it's not still a maximum. It's just not an absolute maximum. It's a local maximum because on some open interval surrounding it, it is the highest point. Okay? Or just like at C, on some open interval surrounding C, it is the lowest point. And so it's a local minimum. Okay? For example, so is D. D is a local maximum. D also happens to be a local and an absolute max. And it's possible for a point to be both a local and an absolute maximum, or a local and an absolute minimum. It's also possible for it to just be local. And also importantly, endpoints are always local maxes or local mins. So these endpoints here at A, this is a local min because everything to the right of it is larger than it. And this is also a local min because everything on the open interval to the left of it is larger than it. Good or no?
Good.
Cool. All right. So now we get into like the whole point of all of this, which we've talked about sort of a few times, but we're going to put some names to things now. A function can have a local minimum or a local maximum at an interior point of its domain. Okay? If the derivative at that point is equal to 0, or at what we call a critical point. So a critical point is a point at which the derivative is 0 or the derivative doesn't exist. And that's something we've already talked about, right? We've said we could have a local minimum when our derivative was 0 because that makes our tangent line 0. And I think we also mentioned we could have a local minimum or a local maximum at a place where the derivative is undefined, right? Like at a cusp or at a corner, we might have a local max or a local min. True? Talked about that before a little bit.
Yeah.
Yeah? All right, cool. So, a very, very important term, a critical point. And they might ask you on the AP test for critical points or critical values. Those points are all of the points that make the derivative 0 or make the derivative not exist. So you want to know those terms. Good or no? Hopefully good. All right, now I've also made this point down here. A stationary point is a point where the derivative is 0. You're not going to need to know that. So let's see if we can find now the absolute maximum and absolute minimum values of this function x to the 2/3 on the interval -2 to 3. And note that this is a closed interval. Okay? So where can we have an absolute max or a min on a function on a closed interval? On a closed interval, the max and the min, the absolute max and the absolute min could be on the interior, right? True?
Sure.
Or they could be at endpoints in the interior, or they could just be at endpoints. Everybody agree with that? So we need to check both endpoints for this closed interval and interior points for this closed interval for our function that we're looking at. So first off, the endpoints, that should be pretty straightforward. The endpoints are -2 and 3. We've already found those, right? So we need to check endpoints, and we need to check every point on the interior, but every point on the interior that could be a max or a min is a critical value. So we need to check endpoints and we need to check critical values. Those are the only places where this function could be at a max or a min. So first off, let's find the critical values by setting the derivative equal to 0 and seeing when the derivative is undefined. So what's the derivative of f of x? What's the derivative of x to the 2/3?
2/3.
2/3? That's what you both said. You both said 2/3. And that's not right. 2/3 x to the -1/3? That sounds better, yeah? Okay, so that could be rewritten as 2/3 times the cube root of x. When does that equal 0? A fraction can only equal 0 if the numerator is 0, right?
Never.
When it's 2, 0.
Never.
Never, right? That's not a trick question. So it never equals 0, but what about when is it undefined? F prime is undefined if 3 cube roots of x equals 0, which would be when x is
0.
0, exactly. All right, so we've got critical value of x equals 0. And we've got endpoints of -2 and 3. So our possibilities are 3, 0, and -2 for places where the absolute max and the absolute min might occur. All we need to do is figure out what's f of 3, what's f of 0, and what's f of -2. And then we'll know which one is the largest and which one is the smallest, and we'll be done. So what is f of 0? That's the easiest one. F of 0 is f of 0 is
0.
0. What about f of 3? That's the cube root of 9, right? And this is the cube root of 4. Okay? So which one of these is the largest? Is cube root of 9 0 or the cube root of 4 bigger?
Cube root of 9.
All right. Has an absolute max of the cube root of 9 at x equals 3. And which one is the smallest?
0.
Wonderful. And so we've determined on this closed interval what the absolute max and the absolute min are. And we should note that we were guaranteed to have both an absolute max and an absolute min because this function is continuous on this closed interval. And so the extreme value theorem says that we must have an absolute max and an absolute min. Everybody good?
Yes.
Cool. All right. Let's see if we can do one more of these before we run out of time today. So f of x equals 1 over, I don't know what happened to my fraction bar there, 1 over the square root of 9 minus x squared. So what should we do? We're not given an interval, so let's think about this function. What is the domain of this function?
Would it be a vertical asymptote at 0? And then
Not
all
at
the
0. So the only things that would make this undefined would be whatever makes the denominator undefined, right? And a couple of things going on there. One, that it's a denominator, so it can't equal 0, right? The square root of 9 minus x squared can't be 0, but it also can't be negative. So 9 minus x squared has to be positive, right? If 9 minus x squared is equal to 0, then we have something that's undefined. And if 9 minus x squared is less than 0, we have something that's undefined. So the domain of this is x squared is less than 9, or x is less than 3 greater than negative 3. So our domain is an open interval. So are we guaranteed to have an absolute max and an absolute minimum?
No.
No, we're not. But we might have we might have one or the other, or we might still have both, depending on what this function looks like. But there's not going to be any endpoints to check since there's no endpoints to the domain. So the only thing we need to look for here is critical values. So I'm going to rewrite this as f of x equals 9 minus x squared to the negative 1/2. I think that'll help us with taking our derivative. And what is f prime of x? Remember, this is u to the negative 1/2, right? So that should be negative 1/2 of u to the negative 3/2. And then times the derivative of our u, right? U is equal to 9 minus x squared. Good or no? Okay. Negatives will cancel, 2's will cancel. So we got f prime of x is equal to x over 9 minus x squared to the 3/2. So first off, when does this equal 0?
if x is equal to 3 or negative 3.
I don't think so. That's not when this equals 0. Only equals 0 if the numerator is 0, right? So only if x is 0. But what about when is it undefined? It's if the denominator equals 0. Right? When does that happen? That happens at x equals, that was the positive or negative 3 you were saying, I think?
Yeah.
Yeah. So the positive and the negative 3, though, if you think about this, these values are not in the domain. And critical values must be in the domain, right? Our domain was negative 3 to 3, not inclusive. And so 3 and negative 3 are not in the domain. So the only place where we might have an absolute max or an absolute min is at x equals 0. Everybody good with that or no?
Yeah.
All right, so then the question becomes, how do we determine if it's an absolute max or if it's an absolute min? Well, at x equals 0, what do we get? F of 0 is 1 over the square root of 9 minus 0 squared. So it gives us what, 1/3? What if we were to plug in something like, something between 0 and 3, like f of, what do you want to plug in there? 1? Okay, f of 1. That's going to give us 1 over the square root of 9 minus 1, or 1 over the square root of 8. Which one of those is bigger?
1/3.
1/3 is bigger than 1 over the square root of 8?
No, it is not. It's 1 over 8.
Yeah, 1 over the square root of 8 is bigger, right? This is larger than 1/3. And so this value that was either an absolute max or an absolute min must be an absolute min. Because the value next to it, 1 unit over, is larger than it. Good or no?
And then there's no absolute max, correct?
Correct, no absolute max. Any questions, issues, problems with that? Everybody okay with that? We're going to do a whole lot more with this in the next couple of days. So you're not actually going to have any homework tonight, which is nice. If you have stuff to make up, now would be a good time for you to do it in the next, day before I start giving you homework again. But that's it for today. Anybody have any questions?